In this video, we're going to be talking about probability and Bayes' theorem, but a brief recap on how we think about sample spaces. As you can recall, if we were to flip a coin, like so, our sample space consists of two things, heads and tails. So we've got one option which is heads, one option which is tails. That's a person, believe it or not. That's some sort of building, right? So this is our sample space, heads and tails, which we can more efficiently denote as H and T. If we were to roll a die, our sample space, let's skip the little drawing here, is the numbers 1 through 6. Which, assuming the die is fair, each have the same probability of happening. So another way to think about the sample space for our die is to sort of draw it a little bit more graphically. We can say draw it as it's splayed out, as if we sort of cut it open. 1, 2, 3, 4, 5, and 6. So each of these squares is equally likely. We can imagine throwing a dart at this sort of cross-shaped board and assuming that we were going to hit somewhere on the board, but that we had no idea where we were going to land on the board, the chance of landing in each of these squares would be 1/6 of the total. So the reason for describing it in this way is that this allows us to motivate sort of a more abstract way of thinking about sample spaces, although using the same basic idea of this sort of indefinitely equally likely dartboard. So let's draw sort of our more abstract dartboard just as a square. And then let's describe some area inside it, which will denote A. So say that A is 1/3 of the area of the square, and saying that we're the world's most erratic dart thrower, so we don't know where we're going to land. The probability of getting A, P of A, in this case would be 1/3. So the reason this is a useful way of thinking about probability is that we can then go from this to thinking about how we would deal with joint probabilities or a sample space with two different outcomes. So let's draw another sample space a little bit bigger. And now we can have A and we can have B. And then we can think about the overlap between the two of them, A and B. So what we might be interested in is the probability of landing in A and B. So it's P of A and B, which if we look at this as, something like 5% of the area. So it's a fairly small probability. But we also might want to be thinking about how do we describe P, A, and B in terms of P of A and P and B and so forth. So the key thing is to think about P of A and B as something that can be arrived at in sequence. That is, first we can arrive somewhere inside A, and then once we've arrived in A, what's the chance that we're going to be in this little area that's just a small sector of A? So the probability of landing inside anywhere in A is 1/3, and if this is maybe 1/10 of A, then the chance of landing in here, given that you've landed somewhere in here, is 1/3 times 1/10 equals 1/30th, right? So this first one here is P of A, and the second one here is P of landing in A and B, given that you were already in A. So of course we can describe this area in the same way, thinking about what would happen if we landed in B first, and then conditional on B, what's the chance that we landed in A? So we might also say it's equal to, that is P, A, and B is equal to P of landing in B times P of landing in A and B, conditional on landing in B. So these two things here and here are both different ways of writing P, A, and B equals P, A, and B. Right? So of course then we can set them equal to each other. So say we want to solve for this thing here, where we set the two of them equal to each other and then we divide through. So the other thing we can say is that the chance of P of A and B conditional on A is equal to the chance of P of B conditional on A. So another way of putting all of this stuff is to say, and this is just notation really, P of A times P of B given A, and this one is equal to P of B times P of A given B. That's just a notation thing, but the key thing is that what that shows is that chance of getting A and B conditional on A is the same as the chance of getting B conditional on A, because the only parts of B that you can land in conditional on A are the parts of B that are shared with A, that is, the parts that are in this little area in between here. So if we set these two things equal to each other down here, let's start with this portion here and put everything in terms of that. So we have P of B given A equals P B times P of A given B divided by P of A. So that's basically Bayes' theorem or Bayes' law or whatever you want to call it in a nutshell. It's a way of going from P of B given A, a way of going from P of A given B, this one here, to P of B given A. And if you're wondering why on earth do we need an elaborate theorem and law for this, well, the lesson goes into that. A lot of times what we have is this thing, and what we need is this thing. So again, if you've got a positive test on some sort of check for a disease or a pregnancy or something like that, often what the test is giving you is this, and what you really want to know is this, not what the chances of getting a marker of pregnant if you are pregnant, but rather what the chances of being pregnant given that you've gotten a marker of testing for pregnancy or testing for just some disease. The other place that all of this comes into play is in quite a lot of later statistics when we're using, instead of A and B, the data that we've got and then some inferences we're trying to make about sort of the hidden parameters of the hidden world. So we'll be trying to go from inferences based on the parameters, that is the likelihood of the data given the parameters, to something where we're interested in the likelihood of parameters given the data. Don't worry at all about what I was describing there. The idea, though, is that we need some way of talking about things we don't know in terms of what we do know, and the way to do that is using Bayes' theorem, which gives us a very nice way of having insights into things we don't know given what we do know.